Okay, so the next couple of things that we're going to talk about for Chapter 8, these are like just vocabulary terms. And in the past, on the study guide, I have just listed them as a part of the vocab matching. But on the test, I don't actually give them as vocab matching. Instead, I put them in as multiple choice questions. So I'm in the process of changing that so that your study guide reflects it. But I'm going to basically tell you what the test question will be for these types of things. Okay? So the first one is bond dissociation energy. That's the energy required to break the bond between two covalently bonded atoms. So it's what breaks it so it goes apart. The units for this energy is usually given in kJ/mole, which is kilojoules per mole, which is the energy needed to break 1 mole of the bond. But we haven't talked about moles yet, so that doesn't really mean anything to you. A large bond dissociation energy corresponds to a strong covalent bond. There are numbers associated with it, and I'm going to show you guys the table with numbers in just a second. But what you're going to have to know is which one takes the most energy, a single bond, a double bond, or a triple bond. So the stronger bond takes more energy. Okay? So somewhere I would write down the triple bond is the largest. It takes the most energy because it has 3 bonds that it has to break. Then next strongest is the double bond. And then the weakest is the single bond. So for a multiple choice question on this test, I'm going to say, which of the following needs the most bond dissociation energy to break the bonds? And it'll be like A, CC single bond, B, CC double bond, C, CC triple bond, D, they all need the same amount. And you guys would just have to pick triple. Okay, so the more lines that are between, the more connections, the stronger it is. Make sense? Okay. So this table has numbers. Then on the video it's going to be really hard to see, but so the CC single bond takes 348 kilojoules to break. For a double bond, it takes 614 kilojoules to break, and for a triple bond, 839. So the number gets higher as you get more bonds, and that's showing you that a higher number of bonds means it needs more energy. It's a stronger thing, so it's going to hold together better. Okay? But you just have to know triple bond's the highest. But I could like switch that around and ask you which one needs the least amount, and then you'd have to pick the single bond. Okay? The next multiple choice question about a vocabulary term is a resonance structure. Resonance structures show that there is more than one way to draw a valid electron dot structure or to have a Lewis structure drawn. And there's more than one valid way to do it. We use chemists use resonance structures to show that the electrons can move around, and sometimes one structure is inadequate because you can have many different versions. This is how, like, when we draw stuff on the board for our Lewis structures, when I draw it in my notes versus how you draw it in your notes, it might not look exactly the same, but as long as you have the correct number of bonds and the correct number of electrons and everything is good to go, it's the same thing. So that's what resonance structure means. Okay? On the test, I'm going to give you a question that has a picture of resonance structures, and I'm going to say, which of the following vocabulary terms best describes this picture? And you'll just pick resonance structure. Okay, so this is what the pictures look like. Where you have different structures with arrows pointing at both ones, meaning that they're interchangeable. Okay, so if we had CO3 minus 2, you have 2 single bonded oxygens to the carbon and 1 double bonded oxygen. What's up? You don't have to. On the study guide, I'm going to have a picture so that you know that it's resonance. If you want to draw it, you can, but you don't have to. But so, for the CO3 minus 2, we have 2 single bonded O's and 1 double bonded O. Okay? So in this first structure, you have single, single, double on the right side. In the middle structure, you have the double on the left side. And then on the final structure, you have the double bonded O on the bottom. So those all 3 mean the same thing, and they're all 3 correct, but they are arranged differently, and so that's why we call it resonance. Okay? So if you have a picture like that, can you pick resonance from the pictures? Hopefully. Okay. The last one, I'm going to give you a lot of background information that's not really necessary in Chem 1, but then you're going to have to label a picture too. Okay? So we have bonding in molecular compounds. In chapter 5, we learned about orbitals like the SPDF, and we said like S is a spherical, and P is a dumbbell, and D is a clover, like that, when they're separated in their atom form. But we also have new bonds that when you have two atoms bond together, the new areas in which the electrons are located have taken a different shape. And that's what we call these molecular orbitals. Okay? So we're going to label a picture about a molecular orbital for the test. So they're making these new shapes for us. And it kind of has to do with how these things are being combined together. Good to go? Good to move on? Okay. So the picture on the right is just like extra information and make it look pretty. That's stuff that if you take AP chemistry, you would have to know more about that, but in Chem 1, we don't need to know about it. But we have bonding orbitals, and all of these orbitals still hold 2 electrons, just like we had 2 electrons on a line when we did orbital notation in chapter 5. So what we're going to have to do is we're going to have to label these like pictures. And there's 2 labels, so it's a 50-50 chance if you're going to get it right or not. And so we'll just have to label those to show what the molecular orbitals look like. Okay? So the first one is called a sigma bond. Sigma, the Greek letter sigma, is that like O thing. Mine, when I draw it, is not that pretty. Mine looks like something like that. It's a lowercase sigma. Sigma surrounds. It's symmetrical. All of these S words are how you can remember the sigma bond. Okay? So sigma bond is usually formed between 2 spherical shapes sometimes. And so we have the hydrogens are both spherical because they're 1s1. And then when they form together to make the diatomic H2 molecule, then the areas that are surrounding these hydrogens form together to make like an oval shape. And so it's surrounding the entire nucleus, the entire molecule. And so that's why we call it sigma surrounds, because it's surrounding the entire area. It's connected. Okay? So yeah, alliteration works great for remember this. So sigma surrounds. Okay? The other type is called pi, the pi bond, where it's made by overlapping p orbitals, which are the dumbbell shapes, and they produce our pi bonds. So we use the Greek letter pi for that. And so the shape here is above and below the regions of the axes of the bonded atom. So it's not surrounding this time, it's above and below our molecules this time. Okay? So the picture that's in your notes on page 6 is going to be very similar to what you're going to have to label on a test. Okay? So for our pi bond, we have them where you have your 2 dumbbells, the 2 P's that form together to make this above and below thing, right? So if we draw a line through the middle, it's above and below. I asked my 3rd hour, because you know we have sigma surrounds, what's a P word that we can help us to remember pi? And somebody came up with parted. So pi bonds are parted. I kept saying separate. They are separated, but they're parted. They're not attached to each other. They're not surrounding, they're parted. Okay? So if you want to write down parted, if that will help you remember it with alliteration, awesome. If you can think of a better P word, let me know. I'll probably use it. Okay? So on the test, you will be given one of these kind of questions, like one of these pictures, one or the other, and you would just have to label it sigma or pi. And you can write out the word sigma and write out the word pi, or you could use the Greek letter, because I know what that means. Okay? Seem pretty hard? Not too bad, as long as you study. Should be okay? Alright. Now, we're going to get back to Lewis structures and the handout I gave you. So, to build on top of our Lewis structures, we have what's called Vesper theory, which is valence shell electron pair repulsion theory. It's pronounced Vesper even though it's spelled V-S-E-P-R. Vesper theory tells us that when we have electrons, the electrons like to be as far apart as possible from each other. Just like a magnet, when you try to put the north and north side together, they repulse each other. Same thing happening with these electrons, okay? And so, normally when we draw on our papers, we just have a two-dimensional shape. But this is three-dimensional world, right? So, we have set three-dimensional shapes to fill in for that. And this is where the handout comes in. The table in your notes, we're not going to fill that in. Because I decided, since it's not on the test, we don't need to worry about it. No, we're going to do example 3, and then we'll be done. But we need to write some stuff down on our handout first, so then we can know how to use it. Okay? So, looking at the handout, we are, and on mine it's in color, sorry that yours is not. We do not need to know about the electron pair geometry column today. That is going to be important on Monday, but it's not important today. Okay? We're just caring about the shapes with names. So like trigonoplanar, bent. Trigonopyramidal, bent. Some of the names repeat. They're not that exciting or crazy. So on mine, the red are the central atoms, so what everything's bonded to. And then the green circles are the atoms that have been bonded. And then the bluish balloon type things are the unshared pairs of electrons. Okay? So we are looking at just the central atom and what has been connected to the central atom. So we are going to write on here 2 numbers by each picture. Okay? And the 2 numbers are going to signify things about our picture so that when we look at a Lewis structure, then we know what we're talking about. Okay? The first number is going to be the number of atoms that are some way connected to our central atom, whether it's double bond, triple bond, single bonded, however many atoms are connected to the central. And then the second number is the number of unshared pairs. Okay? So we are going to count those up, and then when you know that from a Lewis structure, you can look at this paper and say what name it is. Okay? So I'm going to circle my central atoms just because it's easy to see as you get started with this, but you don't have to if you don't want to. So up here at the first linear, the red is our central. So how many atoms are connected to our central? 2. Does it have any unshared pairs? No. So we're going to say that's a 2, 0. Okay. Now for trigonal planar. On our central atom, how many atoms are connected? 3. How many unshared pairs? 0. Okay. Skip the sp2 thing for today. Now our bent. This time we have 2 atoms and 1 pair. It's just like a pair of pants, right? So we have 2 electrons that make 1 pair. So that confuses people sometimes. Okay, next, tetrahedral. What's that going to be? 4, 0. Trigonal pyramidal. 3, 1. And the bent, see, bent repeats itself. This bent is going to be 2, 2, right? Okay, keep moving on. Yep, the next one, the trigonal bipyramidal, will be 5, 0. Sawhorse is going to be 4, 1. T-shaped is 3, I just messed up, 3, 2, and 2, 3. And then the last one, octahedral, 6-0. Okay, square pyramidal, 5-1. Square planar, T-shaped, and linear. Alright. So yeah, I was not the one who came up with these names. They're just accepted generally by the scientific community. It's not from me. Something else to notice from here, which this is going to be more important next week, but not right now, but it kind of does. Like for the octahedral row, the number of things that are connected to the central add up to 6 in every single structure, right? So octahedral has 6, 0, so that's 6 things total. Square pyramidal, 5-1, adds up to 6. 4-2, adds up to 6, like that. So if you would like to, on the side of your paper, by each row, you can write like, it starts with 2 at the first linear. It's 2, 3, 4, 5, 6. Our total number of things connected to the central atom. So if you would like to write that down, you can, but you don't have to. Okay? So what we're going to do with this paper, we're going to do this in example 3, is we are going to write the Lewis structure, like we've been doing all week, and then we are going to count up on the central atom how many atoms, how many unshared pairs, and then we're going to find the name, like square pyramidal, from the paper to name the shape. Okay, so let's try it. So, the first one we have is water, H2O. What's our central going to be? The oxygen. How many dots are on oxygen? 6. Okay, and then we have 2 hydrogens to connect, so go ahead and connect those 2 hydrogens somewhere. Make sure that you connect them at their own dot, not at the same dot. Okay, is that a pretty good, is there anything need to be added to that Lewis structure? Octet complete? Yes. Okay, now we are looking at the central atom. So our central atom is going to be the oxygen. Okay, so we're counting things that are on the oxygen. So how many atoms have been connected to the oxygen? 2. 1, 2. So our first number would be 2, comma, how many unshared pairs are on the oxygen? 2. We have 4 total electrons, but that would make 2 pairs. So it's going to be a 2, comma 2. So what's that called on your paper, on your handout? Bent. Okay, so that's what we're doing there. The HCl. How many dots are on a chlorine? 7. And I have 1 H, so you connect that H somewhere. Do we have a central atom? No. So, this is a trick question. There's no shape, because there's no central atom. Then the last one, NH3. Somebody asked me this earlier, so I'm going to throw this in to the mix, right? So let's say when you make your connections and you're all done, when we're figuring out on the nitrogen, because that's our central atom, what is here, we have 1, 2, 3 hydrogens, right? So it's going to be 3 comma. And then what about these 2 electrons that are not paired up right now? What happens to those? They become a pair. So even though on our papers they are not together, they're not next to each other, they in 3-dimensional space will move to become a pair. So we would still count these 2 as a pair of electrons. So that would be a 3-1. So what do we call a 3-1? Trigonal pyramidal. And if you don't know how to say the names, it is okay. They are kind of weird. Last but not least, we don't have these in our examples, but if you would ever have like a double bond, right? So like it maybe looks like crazy like that or something. If you have a double bond and you're counting atoms, you don't count the lines, you count the the elements that are connected. So even if you have a double bond, this would still be 1, 2 atoms connected. Okay, does that make sense? Another thing, when you're counting up your unshared pairs, we are only looking at the central. So even though, like in this case, the oxygens have unshared pairs on them, those unshared pairs do not matter on our VSEPR handout because we are only looking at what is on the carbon, only what is on the central atom. Okay? So that's where you want to make sure you have a correctly drawn Lewis structure, because then you just look at the central and don't be distracted by all the other dots on the outsides. Okay? Good to go?